Hi everyone, I am Syed Naqvi. I am a PhD student at the Astronomical Observatory. And today the main motive of this talk would be to understand why Einstein is covered with those sort of giggly lines. So the title of my talk is Chaos and Einstein-Rosen waves. So here I would mean the Einstein-Rosen gravitational waves. So this is joint work done with Sebastian Schefter, and recently it was accepted in PRD as a lecture. So before this sort of work started, I was working in standing gravitational waves, but in a different topology. And when I was giving this talk at a student conference here in Eugene, so Professor Yarek, he suggested a motivation which I will tell you now. So you all must have heard about Faraday waves, right? So you can have, let's say a cylindrical, not cylindrical system. You can have some liquid in a vessel. And when you shake it, it will produce some waves, right? And because there is a boundary, there will be some standing waves produced. But at a critical, at some vibrational frequency, when it is greater than a critical value, so this flat hydrostatic surface, it becomes kind of unstable. And when this instability kicks in, so it depends on this parameter gamma, you can have these various Faraday patterns kind of thing. Now, more interestingly, what you can have is that you can have little droplets on it. So you can imagine that this surface is vibrating, and you can have small oil droplets on it. And once you have that, these droplets, they start to vibrate with the liquid, so they are just bouncing, that is fine. But as and when the instability increases, these droplets start to move. So these Cooder droplets, so these are millimetric oil droplets, they actually start to move. And interestingly, and I found this very interesting, that you can do some quantum hydrodynamical quantum mechanical analogs. Like you can have the quantization of orbits, not the quantization which was talked in the previous, like the classical quantization of orbits, or you can do other quantum mechanical hydrodynamical analog experiments. So in that talk, Yarek suggested that if you have a cylindrical standing gravitational wave, how will the particle orbits look like? So previously in POTOR 2022, when Sebastian gave this talk, we studied this problem only, that you have a space-time which has cylindrical standing gravitational wave, and then the geodesics was studied there. And at that time, we found that there were some sensitive dependencies on the geodesics. So we did not found the circularly quantized orbits. We found that the geodesics are showing sensitive dependencies. And the main idea of this talk would be that the first chaotic geodesics were discovered in the last POTOR, but I will show them briefly here. And because if there is sensitive dependencies in a system, then it might suggest that there is some or the other kind of chaos. But how do you go about chaos? Just sensitive dependency does not show that there is chaos. So the other thing which we looked into was the fractal structure, and then to further solidify the concept of chaos in this space-time, we also looked into the pointer maps. And then at the end, the idea would be to understand what these wiggling is happening. So that is important, and that is where the first image I showed that Einstein is surrounded by. So chaos as a concept in gravitational waves has been studied before. It's not new. So Podolsky and Wesley, they studied the chaotic behavior in vacuum PP wave spacetimes. Then in 1973, Friedman, they also studied like if you have test particles in Schwarzschild black hole, and then they are perturbed by a class of gravitational waves, then the orbits are chaotic. Similarly, Suzuki and Taichi, they also studied that chaotic orbits actually emit 10 times more gravitational waves than circular orbits. So this was pretty interesting. Then Cornish also studied that gravitational waves from chaotic orbits, they can be used as a kind of observational perspective. But what I would focus on would be the famous Einstein-Rosen wave solutions. So obviously, the Einstein-Rosen wave solution is, it does not represent any bounded source. So you cannot study any physically relatable, like the gravitational waves which you have been discovering. But the Einstein-Rosen metric is very important because you can use it to test relativity, or it has many uses in the, let's say, in the quantum gravity aspect. So here, the main, let's say, the protagonist of this space-time is these two metric functions. One is the gamma and the other is the psi. So one represents the polarization of the gravitational wave. So this is just a linearly polarized circular standing gravitational wave. The cross-polarized solution was also discovered by Hallenstein. So this was, this Einstein-Rosen solution is very famous because it was one of the first exact solutions to prove gravitational waves in full GR. Before that, Gudiobek has also discovered that. Then, I mean, it is cylindrical symmetry. This is just a figurative cartoon, not literally like this. Then there are the generalizations of the cosmological models. I mean, it has kind of many generalizations, and it is kind of important. And what we are studying are the standing gravitational wave interpretations of this. So generally, standing gravitational waves, they don't have, as yet, any unique definition. So there are very few studies to it. So to begin, there was the paper by Grushik and Sartre. So if you have an electromagnetic resonator, a toroidal electromagnetic resonator, so that will be providing some TBU, right? And at the symmetry center, you can treat it as a flat spacetime, and that perturbations would generate some gravitational waves at the symmetry center. So those were standing gravitational waves at the linear level they were studying at that time. Then actually bodies tried to study the gravitational waves of unsymmetric body rotating about z-axis, but there was the issue that there was lack of superposition, so it was not the full solution. Then Kramer and Stephanie, they were solution, and actually Hans Stephanie formulated this important question, that are there standing gravitational wave solutions to the vacuum Einstein field equations? Then Shipka and Cheslek in 2018, they proposed to define standing gravitational waves, but in some particular in a high frequency limit. Then Shipka and Naqvi, we studied standing gravitational waves in a polarized T3 Gaudy cosmology. And then in this other paper by Gould, Shikora and Shipka, they studied the cross-polarized case. So what I'm studying right now would be only the Einstein-Rosen cylindrical gravitational waves. So here, this is again a cartoon image, that you can imagine that there are these gravitational waves which are going out from the symmetry center and coming back. So they are interacting and forming the standing gravitational waves. So that is the radial coordinate rho. You have z. So rho is obviously greater than 0. T and z goes from minus infinity to plus infinity, and phi is the azimuthal angle. So you can imagine that maybe that this thing is sort of shaking and it's creating some waves and that kind of thing. And here the important thing are the metric functions, which are functions of the time and the radial coordinate itself. And how do you see the standing wave nature is if you look into these special functions. So you have some time part, and that is multiplied by the radial part. So if you have two standing waves, not standing waves, if you have one wave moving in this direction and one in the other direction, you know that you would get some sine spatial part multiplied by some cosine time part. So that gives you the interpretation that this is a cylindrical standing gravitational wave for here, for this case. And what we do is basically we take the geodesic equation as a first order system. So basically the main protagonist would be these equations. So it would be T dot, capital T, rho dot, and capital P dot. So these are like the ordinary differential equations which are governing what is happening with the system, along with the important part that you have some symmetries of the space-time itself. So that gives you that the angular momentum per unit mass is there, and then you have the normalization factor which would be used to reduce these equations and study them how they are looking. So just to mention again that obviously there is a singularity in this space-time at rho is equals to 0, but we don't care about that for now, because we are studying particles with non-zero angular momentum, so they are just moving around this symmetry center. And the idea was that, okay, if you have standing gravitational waves, they are non-linear, and if you are studying some circular orbits around that, how will they look like? Because in Faraday waves, those are non-linear standing waves on the water, right? So if the Coulter droplets are forming something, how would they look like? But here what we found was the onset of chaos, which I will tell you. So just to mention again that the amplitude of the wave is decreasing as you move away from the symmetry center. And near the symmetry center is where you have the maximum perturbation to the test particles. And the perturbations which the particles are suffering very nearby, these play the role of the periodic driving force. So that is what is sort of causing chaos in this system. So what you do is first you look into the sensitive dependencies on the initial condition. So on the left you have let's say I release a particle with some radial velocity and radial distance and velocity, and I see till tau is equals to 300 m, that's the time dimension here. How other trajectories look like. Now what I do is I only change the velocity by 10 to the power minus 5, and I see that for some part initially the trajectory is the same, but at the end the trajectories are totally different. So this and more results were shown by Shipka in the last POTOR meeting, that you have sensitive dependencies on the geodesics. But now once you have that, how can you more, let's say, quantify the onset of chaos in the system? So first we looked into the fractal structure. So how we are plotting the fractal is basically that you have Yeah, so maybe I will take the example which I understand better. So suppose you have a double pendulum, right? So if you can imagine my arm as a double pendulum, you know that if I release it, it will just go like this, right? And for different release angles, I can do one thing is that, okay, if it's going like this and when it rotates, I can mark that time. I can do it more and more number of times, and more I do it, I will see that a kind of a fractal structure appears there, which we do in our double pendulum experimental class. So here what you are doing is that you have this two axes. One is the P, which is actually the rho dot, and you have rho. And here, this as a cartoon image, I am showing that you have a grid of points. You take like many points. You put them into these differential equations, and you evolve how phi looks at the end of, let's say, 100 times, 200 times, so on and so forth. But just remember that the differential equations are in T dot and rho dot, but there is phi dot also there. So that's what we are saying is that you take points in these grids, you can do it with mathematically, and then how the point evolves, and after 100 times or 200 times, how the sort of phi looks at. So in the next image, I will try to show you how we first looked it into the like by mathematics. So this plot, both the plots, they are when the phi, the azimuthal angle, it evolves till 200 times. But on the left, you see that this is like only 8,000 points in Mathematica. So you are seeing some blurred structure. So this is kind of suggesting that, okay, there might or might not be something interesting here. Now, when you increase the number of points, you plot around, let's say, 50,000 points in Mathematica, you see that this structure is getting more refined. But you are getting these kind of fractal structures. You are obviously still not sure. So here now what I will show in the next plot. So the next plot is it's an HD image, so there are like around 2 million points, and how those evolve. And I would like you to just focus on this zone over here, because this shows how these structures, these are like the fractal basins, these are evolving. So this is the final, let's say, the fractal which we got. So on the x-axis you have the radial coordinate rho, and on the y-axis you have p, which is the radial velocity rho dot. And then you took 2 million points, and then you evolved via the differential equations, and you see where they are going. Exactly how we are doing in the double pendulum, right? That's one way to reveal, let's say, this is, let's say, a numerical sort of proof of that there is actually chaos in the system. But are we done yet? No. Actually, you have to go one step more further to actually understand why these fractal structures are coming. And the fractal structure would be you can take this block, you can consider more million points, you can zoom in, you can get the same structure again and again. Right? And now when we wanted to study this system, let's say in more detail, we looked into the Poincare maps. So the example which I am telling you is that in generally Poincare maps, what you do is you are plotting. So if you take the example of, let's say, the sun, moon and the earth, if you plot the trajectories of these three bodies, you know that the three body problem is not solvable, it is chaotic. But if you plot so let's say that the sun is here and the earth is here, and if I am plotting the point when the moon just crosses over here, right? I am plotting a cross section. So you can plot that cross section in the two variables, right? The position and its velocity. So those reveals to you the Poincare sections, which helps you understand these chaotic systems in a better way. So this is what we are plotting over here. So what we initially had was 4 ordinary differential equations in rho, p, t, and capital T. You use this normalization factor, this one, and then you reduce it to three ODEs. Now 3 ODEs represents a 3-dimensional kind of flow. 3-dimensional flow we cannot imagine it. So we go one lower dimension, and how do we do it? We do it with the help of a Poincare section of T mod 2 pi. So what is this would be some 3-dimensional limit. So you have to imagine that the trajectory is somewhere like this, and the sections I am taking it. So suppose this is a section. One particle will go, one point will go with some initial point, and once it crosses this cross section, that is what you are plotting over here. So this kind of gives you the Poincare section. And what is important over here is that you have the existence of numerous periodic points, and these are surrounded by the Kolmogorov-Arnold modular toroids. Because remember that this is 3-dimensional, right? So there would be a toroid formed around these points only, the periodic points. And now what is more important is that once you delve more deeper into this system, is that you have to find the islands of stability, which are surrounded by sort of islands of instability. So what do I mean by that? So you are plotting these Poincare maps. So these are, so once you look at these plot and you point more and more points, you will see that there are these, obviously there are these cam toroids. Here there are these 5 elliptical fixed points, and these arose from the annihilated resonant toroids and are in accordance with something called the Poincare-Kirchhoff theorem. But more importantly, these 5 elliptical fixed points are associated with, or they are accompanied with 5 hyperbolic fixed points. And it's at these points when you zoom in and you explore, you will get to see why chaos is actually coming in this sort of in this system. So a more clear image than this would be this. So this is the image which we have used in the paper. So it's not that clear, but you can see these islands emerging more and more, like the more number of points you take. So what is important over here is that you have these 5 periodic points. So like so 1, 2, 3, 4, right? And what you do over here is that you look into the stable and the unstable manifold. Now, just to let's say UAGA or alert. By manifold over here, I do not mean the GR manifold. What is actually happening is that you have a system of differential equations, right? That system of differential equations, you can write it as a form of a matrix. A matrix will have the eigenvalues and the eigenvectors. And as we do for the case of a double pendulum, in the phase space, you see that those eigenvalues and eigenvectors are coming together or going away from those points, right? If the pendulum is unstable over here, you will see those eigenvalues and eigenvectors going. So that is the stable and the unstable manifold I'm talking here, not the GR. So what you do is you pick one point over here. Let's say you pick let's say you pick P0. So the stable and the unstable manifold, these lead to a very important concept, which are called the homoclinic and the heteroclinic tangles. So what I'm showing you right now over here is the homoclinic tangle. So the stable and unstable manifolds of the hyperbolic fixed point. So you pick this guy over here, P0, and you evolve the cross section. So you have the Poincare cross section and denoted it by it's noted by lambda. So lambda 5 because this is like period 5 orbits. So what you do is you evolve it forward in time and you evolve it backward in time. If you start from this box of points and over here, so what you see is that you go across and you try to see these, you see these tangles happen. So this is one of the important results of our work, that there are these points of stable and unstable manifolds crossing. But the important point is that when they cross at the unstable points, unstable hyperbolic fixed points, they cross infinitely. And this is something related to the horseshoe map or the contour set, which is like one of the more mathematical domains of chaos. And now we can look at the heteroclinic angle. So what you do is you again start with some point over here, and you can see that, okay, if I want to see how the stable manifold of P0, it is intersecting with the unstable manifold of P1, the other point over here. And once you will plot this, you see that there is this chaotic heteroclinic network arising. And now, why this is important? So this is what I was saying, that the image which I showed at the beginning, right? Einstein is like tangle is surrounded by some tangle. So this is the tangle which Einstein is surrounded by, and we have showed in our paper how symbolically it also means. And the most important part would be that once you zoom into these hyperbolic fixed points, the P0 and the P1, so this is where you are seeing that infinite tangle happening. So what is happening over here is, I can explain one aspect of this, is that you have a stable manifold of P0, so one stable manifold, remember the eigenvalues and the eigenvectors, and you are trying to see its intersection with the unstable manifold of P1. And you see that they actually infinitely cross at this hyperbolic point. So this kind of shows that there is actually chaos in this system. So first you begin with sensitive geodesics, then you move on to the fractal structure, and then finally, like the sort of revealing thing that your system actually has chaos is whether or not you have these infinite intersections of stable and unstable manifolds at the hyperbolic fixed points in your system. And I just wanted to mention this, that when Poincare was solving the three-body problem, it is complicated, so and then he only suggested something that he was saying that at these unstable and stable manifolds, they will cross infinitely. I mean, he did not have mathematics at that time, otherwise he would have seen how these are looking. But he actually knew how these would look at these stable and the unstable manifolds. Like, they are crossing infinitely. So this is just, let's say, a symbolic diagram of how the 5-point chaotic heteroclinic network is looking for our system. And this was very interesting because, you are in a space-time which has cylindrical symmetry and there is standing gravitational waves. Obviously, this is not physical. But if you want to study how particles are being perturbed in that space-time, you see that it's not a very simple motion. There is chaos involved, and it was very, interesting to see the mathematics like this time, the dynamical system mathematics arising in GR, which has been studied before for other space-times, but here it was also interesting. So, in conclusion, I would like to say that we studied a linearly polarized cylindrical gravitational waves, which are the Einstein-Rosen waves. We first found the sensitive dependencies that if you change one of the parameters by a very small amount, you see a drastic difference. This leads us to the aspect that what are other signatures of chaos in this particular system. So we probed the fractal structure and we actually found that there is a concrete numerical evidence of chaos in the Einstein-Rosen gravitational waves, cylindrical standing gravitational waves, sorry. And then to further probe, we looked into the Poincare maps and we found out that there are these homoclinic and heteroclinic intersections. And at these these hyperbolic fixed points, these stable and unstable manifolds, they cross infinitely, which sort of cements the concept that, okay, there is chaos in this system. So we found the 5-component chaotic heteroclinic network. And the future work would be to look at a more generalized case. So we have the Jordan-Ehlers components metric, which has both the polarization. So that would be the ellipsoid solution. And we have to look into the effect of polarization, like how will the fractal structure look like. And because I have few minutes, I will talk about an insect. So what happens was that we were looking at this paper. So there's this insect called C. elegans. So if you want to model how these insects are moving, you have different theoretical models. So you have Monte Carlo and so on and so forth. But in this paper by Morrison and Young, they use the chaotic heteroclinic networks to see how that insect is moving. And apparently it fits very well. In their paper, they found a 3-point chaotic heteroclinic network. Here you saw that it's a 5-point chaotic heteroclinic network. It does not mean that the insect and the standing phase are related. I was just interested that the mathematical aspect was pretty interesting. And just to end the talk, this image is generated by Sebastian using Midjourney, which I think is also being used to generate here. So this looks more cool. So I think he inputted I think Einstein with chaotic geodesics hair and all. I also tried it, but I used a very basic artificial intelligence thing. So I just tried chaotic geodesics with forehead and hair flying in chaotic manner and butterfly, so on and so forth. So it's not that great, but it's this. So thank you for listening. Thank you to the organizers for giving this opportunity. And this means hope chaos stays with you, but I mean in a positive sense. So thank you.
Thank you very much for the expressive talk and time for questions.
Thank you. All of that looks quite fascinating, but there was a lot to digest. So, in particular, I missed somehow what this manifold, the stable and unstable manifolds describe.
Yeah. So just to maybe over here. So. Yeah, because this is actually, this is just the first order differential equation, right? So we can write this as a form of a matrix. And when we are solving the differential equation, you can see that you can solve this differential equation with the help of the matrix formulation. That you can see how the eigenvectors and the eigenvalues behave. So those eigenvalues and eigenvectors sort of define how your stable and unstable manifold is. But just one second, I need one backup slide which is useful, which is here. Yeah. So if you have a simple pendulum, you know that there is one unstable point when the pendulum is at the top, and the stable point is when it is over here, right? So if you plot its eigenvalues, so you are looking into the phase space, and in that phase space, like let's say theta and theta dot, you will get these kind of structures over there. The normal phase space which we get. But what do they actually mean is that they are signifying how the eigenvalues and the eigenvectors are behaving. So for this system, because they are not chaotic, the stable manifold would be those eigenvectors which are going into this unstable point, unstable fixed point, and the unstable manifold would be the eigenvectors which are sort of coming out. Now, it's just that if you have a chaotic system, at these unstable hyperbolic now fixed points for a chaotic system, these stable and unstable manifolds, they intersect infinitely. So this is what they mean.
So these manifolds are like auxiliary structures in the description of a phase space.
Yeah, this is just phase space dynamics. We are not like, because we're not interested in directives, we can't do much. In the phase space, how things look like.